In this part, we'll examine another type of pressure vessel, cylindrical shaped pressure vessel or capsule shaped pressure vessel. Again, we'll just need to examine as normal stress and shear stress. So we need to derive the equations to calculate the normal and maximum shear stresses so that you can use them for design purposes or examination purposes. Okay, so let's look at the normal stress first. So do you think the normal stress is the same in all directions in a cylindrical shaped pressure vessel, just like in the spherical shaped vessel? Of course not. This is not spherical. Okay, you will have a longitudinal direction and a hoop direction, and the values will be different along these two directions. Let's look at the longitudinal stress first. Okay, if you have understood the process, like how we derived the stress equation in the spherical shaped pressure vessel, you should be easily realize that the longitudinal direction stress will be the equation to calculate the longitudinal equation. Longitudinal stress will be the same as that of the sigma A in the spherical shaped vessel. Okay, because of what? Because we would just use the same process and the same equation. Okay, the stress would be just equal the load over the area of the thin wall. Okay, and the pressure or the load that can be calculated from the pressure times the projected area. Right. So what is the projected area here in this case? The sketch is here. So the projected area will be just the inner area of the circle, right? So that will be pi r square, right? Then how about the wall area? The wall area, it will be a circle, right? This is pi r square minus r square, or pi r plus r times r minus r. Since the t is much smaller than r, so that's what we assumed. We simplified in the previous derivation. This will be 2 times pi rt. Right. So the stress along the longitudinal direction will be just the pressure times the projected area, pi r square, over the wall area. That is 2 pi rt. So you get PR over 2t, right? PR over 2t, or PD over 4t. Okay, so this is the same equation as our sigma A in the spherical shaped pressure vessel, right? Then how about the hoop direction? In the hoop direction, you have a different case. Okay, you have a different case. The hoop direction is sketched here. You can see that we just cut a section out of the vessel, and the length of this section is delta t. Then let's ask you the same questions. What is the projected area in this case? What is the projected area? The area, the effective area that the pressure is applied on. Is that a circle? It's not a circle anymore, right? It's a rectangle. So the area of this rectangle equals delta x times 2r, right? So this will be 2r delta x. Then what is the wall area? It has two components, right? Two thin rectangles. Each one of them is just delta x times t. Right? You have two of them. So this will be 2t delta x. Right. Then the normal stress along the hoop direction will be P times the projected area, 2r delta x, over the wall area, 2t delta x. So here you will get PR over t, or PD over 2t. Right? So this is actually 2 times the longitudinal direction normal stress. Okay, the equation here. As you compare it with the previous one, okay, you can see that the hoop direction normal stress is 2 times that longitudinal stress. Then with these two results, we can analyze the shear stress, the absolute maximum shear stress at a random point. Again, we need to consider the outer surface and inner surface. What are the difference? The difference is the pressure, right? So again, on the outer surface, you do not have any pressure along the radial direction, but on the inner surface, you will have a radial direction pressure P. Right, so this is the difference. So let's look at the outer surface first of all. Okay, let's cut a random 3-dimensional stress element, as shown here. Right, cut it from the outer surface. You can see that we can split it into 3 planes, and it's subjected to it has 3 stress components. This is the longitudinal stress, normal stress, PR over 2t. Hoop direction 2 times of it, right? This is PR over t, and along the radial direction is 0. Okay, we can split it into 3 planes and then draw a 3D Mohr circle. Right, the first one, you have the green colored. You have PR over 2t along one direction, the PR over t along the other direction. Okay, let's draw this Mohr circle first. Okay, these 2 points will be the first point, PR over 2t. PR over 2t, let's see it here. The second point is PR over t, right? 2 times of it. You get it here. Connect these 2 points. At the diameter, you can draw the first Mohr circle. Okay, the first Mohr circle. So what is R? What is R1? And here you have PR over T, and PR over 2T, right? So the diameter would be PR over T minus PR over 2T, right? So the radius R1 will be PR over T minus PR over 2t over 2, right? This will be PR over 4t, right? So this is the in-plane maximum shear stress in case 1. That is a PR over 4t. How about the second case? Second case, you have PR over t along one direction, 0 on the other direction, right? So the first point is here, second point is the origin. Okay, the center will be here. Connect them and you can draw the second Mohr circle. So obviously the R2 is just here, right? The PR over 2t. Right, so that is the in-plane maximum shear stress in case 2. Right, this is PR over 2t. And let's look at the third case. third case, you have PR over 2t along one direction and 0 on the other direction. A PR over 2t is here, the first point. Second point is origin. Then center. So draw the Mohr circle. So what is R3? Right. Obviously, the R3 will be PR over 2t over 2. Right. That's the PR over 4t. Right. So the in-plane maximum shear stress in the case 3 would be PR over 4t. Okay, compare these three results. Which one is the largest one? This one, right? So that is the absolute maximum shear stress here, right? So that is PR over 2t. Okay. Then let's look at the inner surface. Okay. On the inner surface, if you cut out a three-dimensional stress element, as shown here, right, you will have PR over 2t along the longitudinal direction, PR over t hoop direction, and P here in the radial direction, but it should be negative P, right? It's negative P. So we can draw these three more circles in the same way. Draw it here. So the first one will be the same, right? The first one you have PR over 2t here, PR over t here. Connect them, find the center. You get the first circle, right? So here is PR over t, PR over 2t. So the radius R1 will be PR over 4t, right? Then look at the second one. And here's the in plane will be PR over 4t. And the second one, second case, you will have PR over t along one direction, and on the other direction is not 0, right? It's negative p. Right, so the first point here, PR over t. The second point will be negative p. Right, negative p here. So connect them, find the center. You can draw the second Mohr circle. What is R2? The R2 will be PR over T plus P over 2, right? So that will be PR over 2T plus P over 2. Okay, this is the maximum in plane maximum shear stress in the second case. So it's a PR over 2T plus P over 2. How about the third one? The third one, you have PR over 2T and here negative P. Right? So here is your first point, second point, center. Then you can draw a Mohr circle. Right, the R3 obviously it will be larger than R1 but smaller than R2. Right, so what is the maximum, the absolute maximum torque? Right, the absolute maximum shear stress will be again the second case, right? So that is PR over 2T plus P over 2. And compare it with the previous one, you can see that you just need to add P over 2, right? So this maximum shear stress on the inner surface is larger than the outer surface by half of the pressure. Here, in this slide, you can see that this is just the tau absolute max. The inner surface is PR over 2t, and the outer surface PR over 2t plus P over 2. Okay, in this slide, we summarize all these equations. You can see that instead of 3 equations in the spherical shaped pressure vessel, we need to use 4 equations to calculate the stresses, normal and shear stresses in a cylindrical shaped pressure vessel, since you need to distinguish longitudinal and hoop directions. Okay. If you want to know the strains, you can also derive the 2 equations, 2 instead of 1, or 2 equations, the strain along longitudinal direction and the strain along the hoop direction. Okay. I believe you all can do it. You all can just try to do it by yourself, right? Derive these 2 equations from the 2D generalized Hooke's law.